May 9, 1941, North Atlantic, approximately 300 miles south of Iceland. Commander Joe Baker-Cresswell watches through binoculars as HMS Bulldog's depth charges explode in massive columns of water around the spot where the German submarine U-110 has just dived, and he's calculating whether to order another attack run when something unexpected happens. The submarine's bow breaks the surface at a steep angle, water cascading off the hull as the damaged boat rises uncontrollably from the depths, with its crew apparently unable to maintain depth control. Baker-Cresswell immediately recognizes this as an extraordinary opportunity, because submarines that surface during depth charge attacks usually mean their crews are preparing to abandon ship, and if Bulldog can capture the submarine before the Germans scuttle it, the intelligence value could be immeasurable. Within minutes, U-110's crew is scrambling onto the deck and jumping into the cold Atlantic, while HMS Bulldog closes rapidly, and Baker-Cresswell orders his gunners to hold fire because he wants that submarine intact. And as the German sailors swim away from their doomed boat and are picked up by British ships, a boarding party led by Sub-Lieutenant David Balme rows across to U-110 and climbs carefully onto the submarine's deck, expecting booby traps or demolition charges to explode at any moment. Balme and his team find the submarine's interior in chaos, with water flooding into the lower compartments, equipment smashed by depth charge concussions, and the acrid smell of chlorine gas from seawater mixing with battery acid. But remarkably, the submarine is still afloat, and the Germans apparently abandoned it so quickly that they didn't execute the standard scuttling procedures that would have sent the boat to the bottom within minutes. What Balme and his boarding party discover in U-110's radio room will change the course of the war in ways that will remain secret for decades. Sitting on a small table bolted to the bulkhead is a piece of equipment about the size of a large typewriter, constructed with obvious precision from wood and metal, with a keyboard on the front, a series of rotors visible behind a hinged cover, and electrical wiring connecting various components in ways that aren't immediately obvious to sailors who are trying to salvage anything that looks important before the submarine sinks. Balme doesn't know what this machine is, but he recognizes that anything in the radio room is probably related to communications, and therefore potentially valuable to intelligence services, and he orders his men to carefully remove the device along with all the papers, code books, and technical manuals they can find in the cramped compartments before the rising water forces them to evacuate. The machine that Balme's boarding party recovers from U-110 is an Enigma cipher machine, the device that German forces use to encrypt virtually all their military communications, and which British intelligence has been desperately trying to understand and defeat since before the war began. And while British codebreakers at Bletchley Park have achieved some limited success against certain versions of Enigma used by the German Army and Air Force, the naval version of Enigma that U-boats use has remained almost completely impenetrable because it incorporates additional security features that make breaking the code astronomically more difficult. The capture of this naval Enigma machine, along with codebooks showing current rotor settings and other critical information, represents the most significant intelligence breakthrough of the war to this point, though the full impact won't be understood until the materials reach Bletchley Park, and the brilliant mathematicians and cryptanalysts working there can assess exactly what has been captured. The story of how British codebreakers examine this captured Enigma machine, how they come to understand the nearly impossible mathematical complexity of breaking Enigma encrypted messages without knowing the daily settings, and how a young mathematician named Alan Turing develops the machines and methods that eventually allow systematic decryption of German naval communications, is a story about the intersection of mathematics, engineering, human ingenuity, and the race against time to break codes that are protecting German U-boats as they sink hundreds of Allied merchant ships in the Battle of the Atlantic. Understanding what British codebreakers discovered when they examined captured Enigma machines requires understanding both the elegant simplicity of how Enigma works and the profound mathematical complexity of breaking it, because Enigma represents one of history's most sophisticated pre-computer encryption systems, and defeating it required insights that would lay the foundation for modern computing. When the Enigma machine captured from U-110 arrives at Bletchley Park in mid-May 1941, it joins several other Enigma machines that British intelligence has acquired through various means, including one purchased from the Poles before the war and others captured from German forces in Norway and elsewhere. But this particular machine is uniquely valuable because it's the four-rotor naval version that U-boats use, and which has successfully protected German naval communications from British decryption efforts for months. The team of mathematicians, linguists, chess masters, and other brilliant minds assembled at Bletchley Park to work on breaking German codes approaches the examination of this naval enigma with intense focus, because they understand that penetrating German naval communications could shift the balance in the Battle of the Atlantic, where German U-boats are currently winning by sinking merchant ships faster than the Allies can replace them. The physical examination of the Enigma machine reveals an encryption device that is ingeniously simple in its basic concept, but devastatingly complex in its implementation, and British cryptanalysts who have been studying Enigma through mathematical analysis and limited decryptions now have the opportunity to examine the actual hardware and understand exactly how the encryption process works mechanically. The machine resembles a portable typewriter in size and general appearance, housed in a wooden case approximately 12 inches wide, 11 inches deep, and 6 inches tall that can be easily transported by one person, and the device is clearly designed for field use by military radio operators who may have minimal technical training and who need to encrypt or decrypt messages quickly under combat conditions. The keyboard at the front of the machine has 26 keys arranged alphabetically rather than in the QWERTY layout used on typewriters, and above the keyboard is a lamp board with 26 small windows, each containing a letter, and these lamps illuminate when letters are encrypted or decrypted to show the operator what the output is. The operator types plain text messages one letter at a time on the keyboard, and for each letter typed, one of the lamps illuminates showing the encrypted letter that should be transmitted by radio. And the reciprocal process works for decryption, where the radio operator types the received encrypted letters and the lamps show the plain text. This interface is simple enough that minimally trained operators can use it, but the complexity lies hidden inside the machine where the actual encryption happens. Opening the hinged cover above the keyboard reveals the heart of the Enigma system. 3 or 4 rotors mounted on a horizontal spindle, each rotor being a disc about 3 inches in diameter and less than an inch thick, with electrical contacts on both sides and internal wiring that connects the contacts in specific patterns. The rotors can be removed from the spindle and reinstalled in different orders, and each rotor has an adjustable ring around its circumference marked with letters or numbers that determines its starting position. And this combination of rotor selection, rotor order, and rotor starting positions creates enormous complexity in the encryption that the machine produces. Each time a key is pressed on the keyboard, electrical current flows through the rotors from right to left, and the rightmost rotor advances one position like an odometer, and after the rightmost rotor completes a full rotation, the middle rotor advances one position, and this mechanical stepping creates constantly changing encryption because the electrical path through the rotors changes with each letter typed. The electrical path doesn't end with the rotors. At the left end of the rotor assembly is a device called a reflector that sends the current back through the rotors from left to right along a different path. And this reflector is the feature that makes Enigma encryption symmetric, meaning that typing an encrypted message on a machine with identical settings will decrypt it without requiring a separate decryption mode. The brilliance of this design is that the same machine with the same settings can both encrypt and decrypt, which simplifies field operations because German radio operators don't need separate encryption and decryption procedures. But the reflector also introduces a subtle weakness that British cryptanalysts will eventually exploit. Because the current must pass through the reflector and return, no letter can ever encrypt to itself, meaning that if the plaintext letter is A, the encrypted letter cannot possibly be A. And this constraint provides information that can help break the code. At the front of the machine between the keyboard and the rotors is another component that adds even more complexity to the encryption. A plugboard or steckerbrett that looks like an old telephone switchboard with 26 sockets marked with letters and a set of cables that can be plugged in to swap pairs of letters before and after the encryption passes through the rotors. The plugboard allows the operator to specify that certain letters should be swapped. So, for example, if the plugboard has a cable connecting A and M, then whenever A is typed, it becomes M before entering the rotors, and the encrypted output then has M and A swapped again before lighting the lamp. And this additional permutation layer vastly increases the number of possible encryption keys, because there are millions of ways to select which letters to swap on the plugboard. British cryptanalysts examining the captured naval Enigma calculate the mind-boggling number of possible settings that the machine can use, and this calculation reveals why Enigma has been so difficult to break even with the brilliant minds focused on the problem at Bletchley Park. The German Navy uses a version of Enigma with 8 possible rotors to choose from, and operators must select 4 of these 8 rotors and install them in a specific order, and this selection alone provides 1,680 possible combinations because the order matters and repetition isn't allowed. Each rotor has 26 possible starting positions determined by the ring setting. And with 4 rotors, this provides 456,956 possible starting position combinations. And when multiplied by the rotor selection combinations, the total reaches hundreds of millions of possible rotor configurations. But the plugboard adds another layer of astronomical complexity, because with 10 cables connecting 10 pairs of letters out of the 26 available, the standard setting for naval Enigma, there are more than 150 trillion possible plugboard configurations, and when this is multiplied by the rotor configurations, the total number of possible Enigma settings reaches approximately 158 quintillion different possible keys. This number is so large that it's essentially meaningless in human terms. If every person on Earth tried one Enigma setting per second, it would take millions of years to test all possibilities. And the Germans believe this makes Enigma mathematically unbreakable, because even if the British capture an Enigma machine and understand how it works, they cannot possibly test enough settings to decrypt messages before the settings change, which the Germans do daily at midnight. The examination of the captured Enigma machine and the materials recovered from U-110 confirms what British cryptanalysts have understood theoretically, that breaking Enigma through brute force testing of all possible settings is impossible, and that any successful attack on Enigma must exploit weaknesses in how the system is used, rather than attempting to overcome its mathematical strength through exhaustive search. The codebooks recovered from U-110 are immediately valuable because they show the daily rotor settings, rotor orders, ring settings, and plug board configurations that U-boats are currently using. And this allows Bletchley Park to read German naval traffic for the period covered by the captured codebooks. But once the Germans issue new codebooks or realize that U-110's materials have been captured and change their procedures, the advantage will disappear unless British cryptanalysts can find ways to break Enigma systematically without needing captured settings. This is where Alan Turing's genius becomes crucial to the British code-breaking effort, and understanding what Turing achieves requires understanding both his brilliant mathematical insights and his practical engineering solutions to implementing those insights in machines that can process the calculations fast enough to be useful. Turing arrived at Bletchley Park in 1939, shortly after war was declared, recruited from Cambridge University, where he had already established his reputation as one of Britain's most promising young mathematicians through his work on computability and his theoretical description of what would later be called the Turing machine, a conceptual device that could perform any calculation that could be precisely described by an algorithm. At Bletchley Park, Turing is assigned to Hut 8, the section responsible for attacking German naval Enigma, and he approaches the problem with a combination of pure mathematical analysis and practical engineering that will revolutionize cryptanalysis. Turing's fundamental insight is that while testing all possible Enigma settings is impossible, it's possible to dramatically reduce the number of settings that need to be tested by exploiting patterns in how Enigma is used and by making probabilistic guesses about message content based on German military procedures and patterns. German messages often contain predictable elements. Weather reports follow standard formats. Position reports use specific terminology. Messages begin with standard phrases. And if British cryptanalysts can guess even a few words that probably appear in an encrypted message, this crib can be used to test potential Enigma settings much more efficiently than blind testing. The key is finding a way to test thousands of potential settings against a known crib fast enough that settings can be broken before they change at midnight. The machine that Turing designs to implement this insight is called the Balme, named after an earlier Polish cryptanalytic machine, but vastly more sophisticated and powerful. And the Balme represents one of the earliest examples of a machine designed specifically to perform rapid logical operations on a scale that humans cannot match. The Balme is an electromechanical device standing about 7 feet tall, 8 feet wide, and 2 feet deep, containing 36 Enigma equivalents arranged in 3 columns of 12, each equivalent consisting of a set of rotating drums that simulate Enigma rotors, and the machine is designed to test potential Enigma settings in parallel by simulating how the encryption would work with different settings and detecting contradictions that indicate a setting cannot be correct. The operating principle of the Balme is mathematically elegant, even though the implementation is mechanically complex. When a crib is available, suggesting that a certain plaintext word appears at a certain position in an encrypted message, this creates constraints on what the Enigma settings could have been, because certain rotor positions would create contradictions where a letter would need to be 2 different things simultaneously, which is impossible. The Balme tests rotor positions mechanically by simulating the electrical paths through Enigma with different settings, and when it detects a configuration that creates no contradictions with the crib, it stops and the operators record that setting as a candidate for further testing. The bomb doesn't immediately reveal the correct Enigma setting, but it dramatically reduces the search space from quintillions of possibilities to perhaps a few dozen candidates that human cryptanalysts can then test manually to find the correct one. The first bomb becomes operational at Bletchley Park in March 1940, and while it's slow and unreliable initially, proving the concept works, improved versions designed by Turing and the engineer Harold Keen become faster and more reliable through 1940 and 1941, and by the time the materials from U-110 arrive in May 1941, Bletchley Park has several bombs operating and the capability to break German Army and Air Force Enigma messages with reasonable reliability when good cribs are available. The naval Enigma remains more difficult because the four-rotor version used by U-boats creates additional complexity that requires more sophisticated bomb configurations. But the captured materials from U-110 provide several months of German naval traffic that can be decrypted using the captured codebooks, and this traffic allows British cryptanalysts to study German naval message formats, identify reliable cribs, and develop techniques for attacking naval Enigma once the captured codebooks expire. The intelligence value of breaking German naval Enigma becomes immediately apparent when Bletchley Park begins reading U-boat communications systematically in mid-1941, using the captured codebooks and later using bomb-based cryptanalysis, and the decrypted messages reveal German submarine dispositions, planned patrol areas, rendezvous points for refueling, and reports of convoy sightings that allow the British Admiralty to route convoys around known U-boat concentrations and to vector anti-submarine forces toward U-boats whose positions are revealed by their own radio transmissions. The impact on the Battle of the Atlantic is dramatic. In the second half of 1941, after systematic naval Enigma decryption begins, Allied shipping losses to U-boats decline substantially, while German submarine losses increase as British forces are increasingly able to locate and attack U-boats whose positions are betrayed by their encrypted radio messages. The Germans never realize that Enigma has been broken because British security around the ultra-secret, the code name for intelligence derived from Enigma decryption, is extraordinarily tight, and elaborate procedures are implemented to ensure that German intelligence cannot determine that their codes have been compromised. When ultra-intelligence reveals U-boat positions, British forces never attack immediately, but instead send reconnaissance aircraft to discover the submarines, providing a plausible explanation for how they were located, and when convoys are rerouted based on ultra-intelligence showing U-boat patrol areas, the British invent cover stories about increased radio direction finding capabilities or improvements in radar that might explain how they're locating submarines. The deception is so successful that German Navy cryptographers repeatedly investigate whether Enigma might have been compromised, and they consistently conclude that the mathematical security of the system makes breaking it impossible, and that Allied successes must be due to other intelligence sources. The examination of captured Enigma machines continues throughout the war, as British forces capture additional examples from submarines, surface ships, and land installations, and each capture provides opportunities to examine different variants and to verify that British understanding of how Enigma works remains accurate as the Germans make modifications and updates to the system. In February 1942, the Germans introduce a new four-rotor Enigma variant for U-boats that creates an immediate crisis at Bletchley Park because the additional rotor multiplies the complexity by a factor of 26, and the existing bombs cannot handle four-rotor Enigma efficiently. creating a 10-month blackout period when German naval traffic cannot be read and Allied shipping losses spike dramatically as U-boats operate without British intelligence being able to track them through decrypted communications. The crisis is eventually resolved through a combination of mathematical innovation and additional captured materials. In October 1942, British forces capture U-559 in the Mediterranean and recover new codebooks along with the 4-rotor Enigma settings. And Turing develops mathematical techniques that allow the bombs to attack 4-rotor Enigma more efficiently. And by December 1942, Bletchley Park can again read German naval traffic systematically, and Allied shipping losses decline immediately as convoy routing and anti-submarine warfare become effective again. The correlation between Enigma decryption capability and Battle of the Atlantic outcomes is so strong that post-war analysts conclude that breaking Enigma shortened the war by at least 2 years and saved hundreds of thousands of lives by preventing shipping losses that would have starved Britain and delayed the buildup of forces needed for D-Day. The broader impact of the Enigma project extends far beyond its immediate intelligence value, because the techniques and technologies developed at Bletchley Park lay crucial groundwork for the post-war development of electronic computing, and Turing's theoretical work on computability and his practical experience designing and using the bombs inform his post-war work on computer design and artificial intelligence. The bomb is not a computer in the modern sense. It's a special-purpose electromechanical device designed for one specific task. But it demonstrates the principle that machines can perform logical operations faster and more reliably than humans. And this demonstration inspires Turing and others to envision general-purpose computing machines that could tackle many different types of problems, not just cryptanalysis. Turing's work at Bletchley Park on another machine called Colossus, designed to break a different German cipher system called Lorenz, pushes even further toward modern computing because Colossus uses electronic valves rather than electromechanical relays and can perform its logical operations at speeds thousands of times faster than the bombs. Colossus is arguably the world's first programmable electronic computer, predating American machines like ENIAC by more than a year, though Colossus's existence remains classified until the 1970s and therefore doesn't receive the historical credit it deserves for being a computing pioneer. The combination of Turing's theoretical understanding of computation and his practical experience building machines to perform complex logical operations at Bletchley Park makes him uniquely qualified to design post-war computers, and his designs for the ACE computer and his work on the Manchester Mark I establish many of the principles that underpin modern computing. The examination of captured Enigma machines also reveals details about German industrial capabilities and manufacturing priorities, because the machines are precision devices requiring skilled labor and careful quality control. And British analysts note that Germany is devoting substantial resources to producing tens of thousands of Enigma machines for military use, despite the war placing enormous demands on German industry for weapons and equipment. The decision to standardize on Enigma for virtually all military communications represents a significant commitment to secure communications, and the fact that Germany maintains this commitment even when resources are scarce demonstrates how seriously German military leadership takes communication security, ironically making the system's compromise even more valuable to the Allies, because the Germans never seriously consider that Enigma might be broken, and therefore never implement fallback encryption systems. The human cost of breaking Enigma includes the toll it takes on the brilliant minds working at Bletchley Park under conditions of extreme secrecy and pressure. And Alan Turing in particular suffers from the isolation and stress of work that he can never discuss with anyone outside the highly restricted circle of people with ultra-clearance. Turing's homosexuality, which he makes no particular effort to conceal despite it being illegal in Britain, creates additional stress as he navigates a society that considers his sexuality criminal even while relying on his genius to help win the war. And the contradiction between being valued for his mind while being persecuted for his identity creates psychological burdens that will ultimately prove tragic. The war ends in May 1945 with Germany defeated and the ultra-secret still intact, and the British government decides that Enigma decryption must remain classified indefinitely because the Soviet Union and other potential adversaries continue using Enigma machines or similar rotor-based cipher systems that they purchased or captured from Germany. And British intelligence wants to continue reading these communications without the targets knowing their codes are compromised. This decision means that the thousands of people who worked at Bletchley Park cannot discuss their contributions to victory, cannot receive public recognition for their work, and must watch as historians write accounts of the war that omit the crucial role that ultra-intelligence played in Allied success, because the truth remains hidden behind classifications that won't be lifted for decades. For Alan Turing, the post-war years bring continued brilliant work on computing and artificial intelligence, including his famous 1950 paper proposing what becomes known as the Turing test for machine intelligence, but they also bring persecution that destroys him. In 1952, Turing is prosecuted for homosexuality after reporting a burglary at his home leads to questions about his relationship with another man. And rather than face imprisonment, he accepts chemical castration as an alternative sentence, undergoing injections of synthetic estrogen that are intended to reduce his libido, but which have devastating physical and psychological effects. On June 7, 1954, at age 41, Alan Turing is found dead in his home with a partially eaten apple beside him, and the coroner rules suicide by cyanide poisoning, though the exact circumstances remain disputed, and his death robs the world of one of the 20th century's most brilliant minds, just as the computer age he helped create is beginning. The tragic irony is that Turing's persecution occurs just 8 years after his work at Bletchley Park helped save Britain and win the war, and the same government that relied on his genius to break Enigma and defeat Nazi Germany prosecutes him for who he loves and drives him to suicide through chemical castration that British law required as punishment for homosexuality. The injustice becomes clearer as decades pass, and Turing's contributions to computing become better understood, and the British government eventually issues a posthumous royal pardon in 2013, nearly 60 years after his death, acknowledging that his prosecution was unjust and recognizing his immense contributions to Britain and humanity. The story of British codebreakers capturing Enigma machines and realizing that breaking them would require pure genius is ultimately a story about how mathematical brilliance and engineering innovation can overcome seemingly impossible challenges, how systematic intellectual effort can achieve what brute force cannot, and how one individual's insights can change the course of history even when those insights go unrecognized for decades. The Enigma machine that David Balme recovered from U-110 in May 1941 was one of many captured examples that helped British cryptanalysts understand and eventually defeat German encryption. But the real breakthrough came from Alan Turing's ability to see patterns that others missed, to design machines that could test possibilities faster than humans could imagine, and to reduce quintillions of possibilities to manageable search spaces through mathematical analysis and probabilistic reasoning. Turing's work at Bletchley Park represents one of the first examples of using machines to augment human intelligence on a scale that changes what's possible, and the bombs he designed demonstrate that properly organized machines can solve problems that are utterly beyond human capability, even when the humans involved are themselves brilliant. The progression from Enigma-breaking bombs to Colossus to post-war electronic computers to modern computing represents a direct line of development, and every computer, every smartphone, every digital device traces its conceptual ancestry back to the work done at Bletchley Park to break codes that the Germans believed were mathematically unbreakable. The examination of captured Enigma machines revealed not just how the devices worked, but also what it would take to defeat them. It would take mathematicians who could see beyond obvious approaches, engineers who could build machines to implement mathematical insights, and most of all, it would take someone like Alan Turing, who could imagine entirely new ways of using machines to extend human capability. The Germans were right that Enigma couldn't be broken through brute force testing of settings, but they failed to imagine that someone might find ways to reduce the problem space so dramatically that what seemed impossible became achievable. The legacy of breaking Enigma extends far beyond World War II, because the techniques and technologies developed to defeat German encryption laid foundations for modern computing, cryptography, and information security. And the story demonstrates how intellectual effort directed at seemingly impossible problems can achieve breakthroughs that change everything. Alan Turing's tragic death at 41 robbed the world of decades of additional contributions he might have made to computing and artificial intelligence. But his work-breaking Enigma and his theoretical contributions to computing ensure that his influence continues shaping the digital age even decades after his death.